Hello and welcome to the fourth video of the FP2 chapter Complex Numbers. P2 review on the screen here. Expand this bracket using the binomial theorem. What we need to remember here is that we're using the x term power 5 times the y term power 0 multiplied by the constant that relates to the numbers in Pascal's triangle. The next one is 5 choose 1, which is a 5 for the constant, x power 4, that goes down a power, and the 2 goes up a power, and then 5 choose 2 is 10, x goes down a power, 2 goes up a power, 5 choose 3 is 10 again, and we continue the pattern until we get to the end. And then you should simplify and put it all together, but for the sake of time I won't do that. We've got some long examples in this video to go through. So we're going to use de Moivre's theorem to derive trigonometric identities. And there's an endless number of trigonometric identities you could be asked to derive in an exam. They fall into two general types that you need to be aware of. The first one is expressing cos n theta or sine n theta, where n of course is just going to be a number depending on the question, in terms of powers of cos theta or powers of sine theta. And this is used both de Moivre's theorem and the binomial theorem, hence the starter question to review this. The other type is basically the same thing but backwards. You need to be able to express powers of cos theta or powers of sine theta in terms of cos n theta or sine n theta. And this is a bit more involved because it uses very specific results from de Moivre's theorem that we'll have to look at, and also still the binomial theorem. So we'll go through this one first, and then we'll look at the specific results needed for this one, and then we'll do a couple of examples from this one. So to express cos n theta or sine n theta in terms of powers of cos theta or powers of sine theta, there's a systematic method. You start with r equals 1 and an appropriate n in de Moivre's theorem. The n, of course, will be related to the question you're trying to answer, but each time you'll use r equals 1. Then you'll need to expand the bracket that you get in de Moivre's theorem using the binomial theorem. Finally, you either equate the real part if you're looking for cos, or the imaginary part if you're looking for sine of the expression that you end up with. So this is a very systematic method. You follow the same method every time. So the method is up here in the corner, and we'll do just one example of this because it's the same every time. Use de Moivre's theorem to show that cos 6 theta, so my n will be a 6, is equal to this expression. So we start with de Moivre's theorem with r equals 1. So we just have cos theta plus I sine of theta raised to the power of n. In this case we're going to use 6, and that equals cos of 6 theta plus I sine of 6 theta. That's our starting point. Obviously the right hand side is looking pretty good. This is the thing that we want, which is why later on we're going to equate the real part, not the imaginary part. But this side here, this is where the work is going to be. I'm going to need to expand this using the binomial theorem, which is going to be quite a long expression. Then we're going to need to tidy it up and then equate it. So let's get going with this. We're going to have cos 6 theta, and then we're going to have a 6 cos 5 theta times I sine of theta, and then the next one in Pascal's triangle here is a 15 cos 4 theta I squared sine squared theta plus 20 cos 3 theta I cubed sine theta cubed plus 15 again cos squared theta I 4 sine 4 theta plus 6 cos theta I to the 5 sine to the 5 theta plus on the end just I to the power 6 sine to the power 6 theta. And you can immediately see why sometimes these questions take a bit of time. Now we need to simplify this, specifically meaning the i's, because this term here, although it has an I in it now, when we simplify this that will be a minus, this will be one of the real terms. So we'll need this. So go through and simplify the terms, and that gives us cos 6 theta plus 6i cos 5 theta sine theta minus 15 cos power 4 theta sine squared theta minus 20i cos cubed theta sine cubed theta plus 15 cos squared theta sine power 4 theta plus 6i cos power 5 theta sine theta minus sine power 6 theta. Now we can equate the real part of this expression with the real part of the right hand side of this equation, which gives us cos 6 theta minus 15 cos 4 theta sine squared theta plus 15 cos squared theta sine power 4 theta minus sine power 6 theta must equal cos 6 theta. Now unfortunately we do have a bit more algebra ahead of us, because this doesn't quite look like this, but we can change sine squareds, and here 2 lots of sine squared and here 3 lots of sine squared, into 1 minus cos squared, giving us cos power 6 theta minus 15 cos power 4 theta 1 minus cos squared theta plus 15 cos squared theta 1 minus cos squared theta squared minus 1 minus cos squared theta cubed is all equal to cos 6 theta. The only thing left to do then is to follow through on simplifying this out. Plus 15 cos power 6 theta minus 15 cos power 4 theta. This bracket here gives me 1 minus 2 cos squared theta plus cos power 4 theta. So expanding that with the 15 cos squared gives us 15 cos power 6 theta minus 30 cos power 4 theta plus 15 cos squared theta, and this one is this bracket times by this expression. First term here, and then we've got minus 3 cos power 4 theta plus 3 cos squared theta minus 1 equals cos 6 theta. And the last thing to do is to tidy this up, and that should give us this result here. So we've got 15, 30, 31, 32 cos power 6 theta minus 15 minus 45 minus 48 cos power 4 theta (15, 18 cos squared theta) and of course on the end a minus 1. Whew, quite a lot of work, but very little in the way of problem solving. Follow the method each time, be very careful with your algebra, and you'll get the right answer. Okay, only one of those examples because it is the same every time and it is quite a long question. So let's move on to the opposite, expressing powers of cos theta or powers of sine theta in terms of cos n or sine n theta. To do this, we need to look at some more general results, but still with r equals 1. What we need to use is z is equal to this thing, and then these three expressions here. And of course we know if z is equal to cos theta plus I sine theta, then z to the n, using de Moivre's theorem, is cos n theta plus I sine n theta. And 1 over z is equal to z to the minus 1. And we proved using Euler's relation and the exponential form that de Moivre's theorem is true for negative integers as well as positive. So we get cos minus theta plus I sine of minus theta, and then those properties we use so often to get the plus in there, we're going to use those again to simplify this to cos theta minus I sine theta, so that we can combine the sine theta with this sine theta later. 1 over z to the n, z to the minus n, gives us cos of minus n theta plus I sine of minus n theta, and we do the same thing. Cos of n theta minus I sine of n theta, so that that can interact with this. Now where we go from here with these might seem a bit strange, but bear with me, it does come together in the final method. So we're going to consider these results here. Z plus 1 over z. So this thing plus this thing, you can see that the I sine thetas will cancel out, and we'll double up on the cos theta. So that will give us 2 cos theta. Then z minus 1 over z, kind of the opposite effect. The cosines will cancel out, and this minus this will give us 2I sine theta. Then we do the same thing with the power n on it, and we get the same sort of thing coming out. 2 cos n theta, and when you subtract them, 2I sine n theta. Now that is going to seem a bit random, but the point of this is that we've got these two expressions here, which are going to be our starting point for the next method, and these two expressions which are going to be really helpful right in the middle of our method. And these four are so important that you just need to be able to recall them. Either memorize them or be able to reproduce the work that I just did there very quickly, because you'll need to be able to use these in your exam if you get a question like this. So we're expressing powers of cosine or powers of sine in terms of one of these. So the method is as follows. We start with either this result or this result to the power of n, and we need to choose that depending on what the question is. Then you expand this bracket as it is with the z's and the 1 over z's using the binomial theorem. And that will give you a whole bunch of z to the power of something and 1 over z to the power of something. So you group those in their respective powers in order to replace those expressions with this, or these expressions with this. Then all you need to do at the end is to tidy things up, so there will be an unwanted constant at the end. Divide through by that, and you'll have your answer. And again, that might seem a little bit daunting, but it's very systematic. If you know the method, just follow the method and it will work every time. So the method here, squished up there, the results here that we're going to use. The question, express cosine power 5 theta in the form this, where a, b, and c are constants to be found. So this is using this expression here to begin with. Simply because that equals this. And on the right hand side, that will give me 2 to the power 5, which is 32. And the bit that I'm interested in, cosine power 5 theta. So this matches what I need in the question. That's great. 32 I'll deal with at the end. But now, the bulk of my work, I need to expand the left-hand side of this original equation using the binomial theorem. So we've got z plus 1 over z to the power 5. And that is equal to z power 5 plus 5 z to the 4 1 over z plus 10 z cubed 1 over z squared plus 10 z squared 1 over z cubed plus 5 z 1 over z to the 4 plus 1 over z to the 5. And I hope you can see that every time you do this, because you've got z's and 1 over z's, they will interact to give you pairs because of the symmetry of the binomial theorem. So here we've got z to the 5 plus 1 over z to the 5. Group them together. Then we've got 5, if you cancel this, z cubed, and 5, 1 over z cubed. And then in the middle, we've got 10z plus 10, 1 over z. And you'll find that happens every time. That's really useful then, because we've got these expressions here. So z5, 1 over z5, add them together. We know from the work that we just did, if you can recall this result, that that is equal to 2 cosine 5 theta. And then here, the same idea, this is equal to 2 cosine 3 theta. Don't forget about that 5 in front. So this is 10 cosine 3 theta, and this one is 2 cosine of theta with a 10 in front, so that's 20 cosine theta. And we know that this equals this, therefore this I can now say equals 32 cosine power 5 of theta. Now I'm on to my last step, just divide everything through by 32 to give me cosine power 5 theta is equal to 1 over 16 cos 5 theta plus 5 over 16 cosine of 3 theta plus 5 over 8 cosine theta, where a, b, and c are 1/16, 5/16, and 5/8 respectively. This method takes a little bit more work to get the method, but once you've got the method with the results here, you can see that the process of actually answering a question is not quite as long as the previous one, because this will end up grouping very nicely and being replaced with the result that you've got. So I'll do one final example of this, and it will lead into one of the reasons why this is so useful, and that is integration. So we need to express sine power 4 theta in the form of this, where a, b, and c are constants to be found, hence find the exact value of this. Now this is really quite annoying to integrate if you don't have this method, because it's not as simple as raising the power by 1 and dividing, because you know sine and cosine interact when you integrate and differentiate. So being able to change this into something like this, single powers of cosine, regardless of the fact that the arguments are now different, is really useful when you want to integrate something. But first we need to do the work to get that expression. So for sine, we're going to need to use z minus 1 over z. And we want power 4, and that will equal 2i to the power 4, which is a nice simple 16, sine power 4 theta. And then this thing here, we need to expand it, which gives us z to the 4 plus 4z cubed minus 1 over z plus 6z squared minus 1 over z squared plus 4z minus 1 over z cubed plus minus 1 over z power 4. Simplifying and collecting the results, we get z power 4 plus 1 over z to the 4 minus 4z squared plus 1 over z squared plus 6. Now we will replace our expressions with the known results here. So z power 4 plus 1 over z to the 4 is 2 cosine 4 theta. And then we get 2 cosine 2 theta times the minus 4, so we get minus 8 cosine 2 theta plus a 6. But remember, that equals 16 sine to the power 4 theta, and we want sine power 4 theta without the 16, so dividing through gives us sine power 4 theta is equal to 1 over 8 cosine 4 theta minus 1 over 2 cosine 2 theta plus 3 over 8. And that is our final expression for sine 4 theta. Now we can go ahead and put this expression into this integration, and the integration becomes much easier. So I'll do that on the next screen. There's our result up there. Putting it in, we get the integral from 0 to pi by 2, 1 over 8 cos 4 theta minus 1 over 2 cos 2 theta plus 3 over 8 d theta. And now this is just as simple as integrating a cosine into sine, dividing by the constant. And that gives us 1 over 32 sine 4 theta minus 1 over 4 sine 2 theta plus 3 over 8 theta. Evaluating that, from 0 to pi by 2. Now these are two very nice limits, because we know that if you put a 0 in here, here, and here, all of that's going to be 0. But also if you put pi by 2 in here, times it by 4, that gives you 2 pi. Sine of 2 pi is 0. Put it in here, 2 times pi by 2 is pi, sine of pi is 0. So out of all of that, the only term that is non-zero is 3 over 8 theta, where theta is pi by 2. So if I make all of that really clear, I get 0 minus 0 plus 3 pi by 16 minus 0 plus 0, which of course is just 3 pi by 16, a really nice, simple result for something that was quite a horrible integration. Now some of these questions can be quite long, especially using that first method going from cosine n theta or sine n theta into powers. Just be really careful with your algebra, it's very easy to make a small mistake. Questions you can practice in exercise 3D, take a bit of time, and maybe I'll see you in the final video for this chapter.